Bismillah ar-Rahman ar-Rahim. Our lecture today is about interpolation. And if you remember the first page of this chapter, it was about the description or the classification of the data points into two categories. The first category is the noisy data points, and for those noisy data points, we have used the regression, and for regression the curve generated through regression technique should not pass through all of the data points, and it should only detect the trend or the pattern of the data. So this is regarding the regression. Regarding the interpolation, as we mentioned also previously, regression is used with accurate data points, and the resulting curve from interpolation polynomial, should pass through all of the data points based on the fact that the data points, they are error free or they are accurate. So again, as we mentioned, interpolation is used with accurate data points, and the resulting polynomial or the resulting interpolating polynomial should pass through all of the data points. And if we consider that we have a general nth order interpolating polynomial, it as given in equation 4.44, where f of x is given as an nth order polynomial of order n. And if we pay attention to this polynomial, it's obvious that the coefficients for this polynomial, they are from a0, a1 till we reach an. So the number of coefficients for an nth order polynomial is n plus 1. And in order to solve this polynomial uniquely, we need n plus 1 data points. We need n plus 1 data points. So if regarding the rule that's mentioned on this page, if we have n plus 1 data points, the rule says that there exists a unique nth order polynomial. So there is a difference, always a difference of 1 between the order of the interpolating polynomial and the number of data points. The number of data points should be 1 higher than the order of the polynomial, the interpolating polynomial. And so for n plus 1 data points, there exists a unique nth order polynomial, and this polynomial, it fits those data points. What does this mean? This means that it should pass through all of the data points. So this means that if we have a given set of data points n plus 1, the generating polynomial using interpolation technique should be unique, and this uniqueness is regardless of two major facts. The first one is the order of the data points. The order of the data points. So if we have any given set of data points from x0 f of x0 till xn f of xn, the order of those data points should not affect the generated polynomial. And if we keep changing the order, or shuffling the data points, the final polynomial will be the same regardless of the order of the data points. So this is the first fact regarding the uniqueness of the interpolating polynomial. The second fact that is related to the uniqueness, it's regardless of the method of generating the polynomial. So we will discuss two major and main methods for generating the interpolating polynomial, and whether we use the first method or the second method that we will describe today in this lecture, the same polynomial will be obtained regardless of the order, regardless of the method of generating the polynomial, whether it's the first method or the second method. So again, if we have n plus 1 data points, and we have generated, as given in this rule, if we have n plus 1 data points, so there is a unique nth order polynomial. So generated polynomial will be of order n, and this polynomial should be unique, and this uniqueness should be regardless of two major facts. The first one is the order of the data points. If we change the order, keep shuffling between the data points, this will not affect the final generated polynomial, okay? And the other fact, that's regardless of the method of generating a polynomial. If we generate this polynomial, interpolating polynomial of order n for n plus 1 data points using the first method or the second method, the final polynomial will be the same, okay? And when we keep changing the data points, we mean we are shuffling the pairs as they are given. We are not changing the base points. We are not changing the base points. So what does this mean? That assume that we have x naught f of x naught and x1 f of x1, okay? So if I provide you with this as the first data points and this as the second data point, and from those two data points we can generate a first order or a line or linear interpolation, okay? So if I give you this is the first data point and this is the second, okay, those pair of data points, okay? So and we solve and we find the linear regression curve, which is a straight line, and we calculate this straight line equation, and then I change the order. And I provide you with this as the first data point and this as the second data point. So the same final polynomial will be obtained. But we should not misunderstand the thing. What do we mean by misunderstanding? Misunderstanding means that the base points should be the same. That I should not give you x naught and f of x1 and x1 and f of x naught. So this is not allowed. This process is not allowed because I am changing the base points. So x naught should be with f of x naught, not f of x1, and x1 should be with f of x1, not f of x naught. So while shuffling, we should keep the pairing process as it is. X naught, f of x naught. Change it whether it's the first or the last, it does not affect. xn, comma f of xn. Also change it, put it in the first, second, third, or the nth position. It does not change. But we should not change like x naught and f of x2, and this is a new pair or a new data point, or x naught and f of xn. So this is what we mean by this fact that the base points should not be changed. Okay. So let us continue the examples in this page. Okay. So if we have two data points according to this rule, if we have two data points, then first order polynomial or straight line will be generated. If we have three data points, then a second order polynomial or a parabola will be generated. If we have four data points, we have third order polynomial or cubic polynomial. So this curve represents two data points connected with a straight line. This curve or figure represents three data points connected with a parabola, and this last one represents four data points, and the curve that fit them, okay, is a cubic polynomial. Okay, so these are the main facts about the rule and the limitation of the order and the method of generating the polynomial. So now we will cover the first method of generating the polynomials. This first method is called Newton divided difference interpolating polynomial. Newton divided differences. And in order to understand it, we will start with a very simple case, which is the linear interpolation. As I said, linear interpolation, which is the simplest form of interpolation, connect two data points with a straight line or linear interpolation. Okay, so assume that we have a pair of data points, two data points, x1, f of x1, x naught, and f of x naught. Okay, so the slope between any two points on this straight line will be the same. And this is shown in this figure 4.9. Okay, so this is f of x naught, f of x naught. This is x1, f of x1, and this is x and f of x. Here it's x, f of x, and here this point is x. So the slope of between those two, the slope between this point and this point is equal to the slope between this point and this point, and the slope of this point and this point. So any two points connected, or any two points lying on this straight line, they will have the same slope. And based on that, we return back to equation 4.45. This is the slope f of x1 minus f of x naught divided by x1 minus x naught, and this is the slope of the line connecting x naught f of x and x naught f of x naught. So if we arrange this equation, we get the final formula for the linear interpolation, and f of x will be f of x naught plus this term, which is the slope, multiplied by x minus x naught, and this slope term, we will call it in this method as the first divided difference, and we will give it this simple according to equation 4.47. F square bracket x1 x naught is equal to f of x naught minus f of x1 minus f of x naught divided by x1 minus x naught. So the first divided difference is equal to the slope. Here there is a very important point, that this first divided difference is an approximation for the first derivative. Okay, and we know that the smaller the interval between the data points, the better the approximation. Okay, we know according to the calculus courses that if the interval between x naught and x1 is shorter, then the slope of the line connecting those 2 points will be close to the actual value of the slope, which is actually the tangent at any point that we need. Okay, so this is regarding the first order interpolation or linear interpolation. And let us take this example 4.10. Assume that we want to estimate the natural logarithm ln of 2, and we will estimate it based on linear interpolation. And we will use two scenarios for linear interpolation. In the first scenario, we will fit between those 2 points, x is equal to 1 and ln L1 is equal to 0, and x2 is equal to 6, and the ln of 6 is 1.79. And then we will repeat the procedure, but we will shorten the distance between the base points. Instead of using 1 and 6, in the first case we use 1 and 6, and we find their function values. In the second case we will use the same one, okay, which is here, ln 1, and we will shorten the distance, and we will use the other one as 4. So in the first case 1 and 6, which is farther away from each other, this is x values in the first example, or in the first case, while this is the x values in the second case. So in the second case, the x naught is equal to 1 while x1 is equal to 4. In the first case, x naught is equal to 1 while x1 is equal to 6. So we can tell that this result, the linear interpolation based on this, since it's closer, will be better approximation than the linear interpolation for the first case. So here the solution between 1 and 6, we have this is the first order polynomial, and we estimate it at 2, at x is equal to 2, and finally we will get this answer, and it has a relative error because here the true value is given, which is equal to 0.69 something. Okay, of this true error, the true relative percentage error is 48%. Between the other pair of data points, x0 and x1, between 1 and 4, we have the same calculation for f1 at x is equal to 2. We have this value, and the true percentage relative error is reduced to 33% from 48%. Okay, and this figure clarify the things. This is the original curve, the black one, and this is the first scenario based on x is equal to 1 and x is equal to 6, and this is the second scenario based on the same x1, x0 as at 1, and the other point is here, which is equal to 4. So it's obvious that this line has a better approximation than this line, and the shorter the distance, okay, here between 1 and 4, it's much better, it has better approximation than when we are using between 1 and 6, between 1 and 6. So this is a validation of the concepts that on the previous page that we have discussed in a few minutes. So we will switch now to the general form of Newton divided differences polynomials. So the nth order polynomial, and as we discussed the rule, if we are speaking about the nth order polynomial, then there should be n plus 1 data points, and those data points from x0, f of x0 till xn and f of xn. Okay, so this is the generated nth order polynomial based on Newton polynomial, and this is its formulation as given in equation 4.48. So if we pay attention to this polynomial, the first term of this polynomial is a constant, b naught. All of the b's, they are constant. All of the b's mentioned here, all of the b's from b naught till bn, they are constants. What I mean, they are numbers. Okay, so the first term of this polynomial as given in equation 4.48 is b naught, and it's constant, certain number. The second term is this one, b1 x minus x naught. So b1 is constant, while x minus x naught, it gives us the linear term, the first order power. So we are switching from constant to first order polynomial. The third term, this one, if we simplify this term b naught x minus x naught x minus x1, we will get constant first order term and second order term. So if we simplify this term, we will get a polynomial of order 2 containing constant power 1x and power 2x, power of x to the power 1 and x to the power 2, and so on until we reach to the last term. If we pay attention to this last term, okay, the x is multiplied how many times? It's multiplied n times. So this means that it's an nth order polynomial. and this nth order polynomial, it will contain all of the coefficients from the constant x to the power 1, x to the power 2 till x to the power n. Okay, so again, let us focus. The first term, b naught, is a constant. The second term take us from the constant term to the linear polynomial. The third term, which is this one, take us from the linear to the quadratic. The fourth term, it will be cubic, and so on till we reach to the last term. The last term will shift us from n-1 polynomial to nth order polynomial. So as I mentioned previously, that all of the b's here, they are constant, they are numbers. b naught is f of x naught, while b1 is the first finite divided difference, and we give it this symbol f of square bracket x1 x naught, while b2 is the second finite divided difference, and we give it the symbol f of x2 x1 x0. And finally we reach to bn, which is the nth order finite divided difference, and this we have given it the symbol of f square bracket xn till x naught. So if we count the number of points for each divided difference, for first divided difference we have 2 points. For second divided difference we have 3 points. For nth order divided difference we have n plus 1 data points, n plus 1 data points. And as we said previously, for certain divided difference it corresponds to the same order of the derivative. What do we mean by this? First divided difference is an approximation for the first derivative, while second divided difference is an approximation for the second derivative, till we reach to the nth divided difference. It's an approximation for the nth derivative. Okay, so we have introduced those divided difference, and now let us see what about their mathematical calculation procedure. So the first divided difference, which is in general for any two nodes f of xi xj, is equal to f of xi minus f of xj divided by xi minus xj. So this is the first divided difference for any pair of data points, xi and xj. Okay, the second divided difference for any 3 data points, as I mentioned, okay, it will be xi, xj, and xk. So how we calculate the second divided difference? It's the difference between two first order divided differences. If we go back to our physics background, okay, we know that velocity is the difference between two positions with respect to time. And we know that if we go up, we know that acceleration is the difference between two velocities over an interval of time. And if we move up, we know that jerk, which is the third order derivative of position, is the rate of change or the difference of two given acceleration values with respect to time. So this is the same procedure. For second divided differences, we should use 3 data points. So we assume xi, xj, and xk. And for their calculation, we will use 2 first order divided differences. 2 first order divided difference. The first divided difference will be xi, xj, while the second divided difference will be xi, xj, xk. And in the numerator, we have xi minus xk. Okay, so how can we generalize this process for any order of the divided difference. I will explain it in equation 4.52. In equation 4.52, this is the general formula of nth order divided difference. Okay, so an nth order divided difference, it should use n plus 1 data points. And it's the difference of two n minus 1 divided differences. This is the first divided difference of order n minus 1, and this is the second divided difference of order n minus 1. So how can we formulate the general formula? The general formula will be constructed as following. For the first divided difference to be used in the right hand side, it should be all the divided difference of all nodes except the last one. So here we are using x1 till xn. So all of the nodes except the last one. And the second, this one, the second, it uses the divided difference from the last till the second without the first one. So this one utilize all of the data points except the first node, while this one utilize all of the data points except the last one, x naught. And we divide in the denominator the first node minus the last node. So we subtract this xn minus x naught. If we go back to equation 4.51 in order to clarify this, so here if we calculate this second order divided difference, it will be the difference between two first order. The first one of those first order will be this one, those two, without the last, without xk, while the second one here, it will be the divided differences from the last till the second without the first. And in the denominator, we subtract the first node minus the last node. So this is the general procedure how to calculate the divided difference of any order. The divided difference of any order. And let us proceed. Here we assume that we have 4 data points from x0 till x3, and their values f of x0 till f of x3, they are given. So the calculation of the finite divided differences, it's of recursive nature as appear in those equations. So we cannot find, for example, the third divided difference without the calculation of the second divided difference. And we cannot calculate the second divided difference without the calculation of the first divided difference. So we should proceed from the first and calculate all of them. Then the second, calculate all of them. Third, calculate all of them till we reach the final order of the divided difference, which is equal to the number of data points minus 1. So we have here 4 data points. We have 4 data points. So the highest divided difference order is third because it's less than the number of data points. The highest divided difference is less than the number of data points by 1. So 4 data points, it means that we can go up to the third divided difference. So if we for the first divided differences, we calculate 3 first divided differences: f of x1, x0, 2, 1, and 3, 2. And based on those, we calculate 2 second order divided differences: f of x2, 1, 0, and f of x3, 2, 1. And based on those 2 second order divided difference, we have a unique and only 1 third order divided difference that utilize all of the data points from x0 till x3. Okay, so if we continue and rewrite the nth order polynomial based on the Newton method as given in equation 4.53, okay, and substitute the values of b's using the divided difference. So this was B0, this was B1, this was B2, and this was Bn in the previous equation. If you remember this equation 4 point, this one, this equation 4.48. It was in terms of b's. Now we'll express this equation in terms of the divided differences. So in terms of the divided differences, it's written in equation 4.53. And as I mentioned previously, that this is a constant term. This will add linearity, first order power of x. This will add x to the power 2 to the previous one. This will add x to the power n to the previous terms. So if we pay attention to this Newton divided difference, it has the following characteristics. Number one, the data points to be used, they are not necessary to be equally spaced. Equally spaced, what I mean by equally spaced, that the difference between any two subsequent data points, it's fixed, it's constant. No, it might be not equally spaced. So this means that if I have xi minus xj for any I and j values, it's not necessary to be h. So this is the first notice. The second, the values of the dependent variable, which is equal y, should not be organized or sorted in ascending or descending order. We can have, as I mentioned, regardless of the order. So the order is not necessary that I should sort the nodes available, okay, the data points available in ascending or descending order. Any random order of the data points, it will result in the same unique final interpolating polynomial, and this is what I have mentioned in the previous minutes. And based on that, there is no need for any sorting process for the data points from ascending or descending. No, any random, okay. So the third note, the finite divided differences, they are of recursive nature, as I mentioned. So assume that we want to calculate the third order divided differences as given in the previous page. We cannot find the third order divided difference unless we calculate at least two second order divided differences. And we cannot calculate any second order divided difference until we calculate at least two first order divided difference. So it's recursive. So it means that we cannot go to any higher order differences without the calculation of the lower order one. And this can be exploited, this feature, to develop an efficient computer algorithm for programming aspects. So the next feature, if we have an nth order polynomial given in Newton's form. What is in Newton's form? This is the form. Newton forms is according to equation 4.53 or the previous equation. Okay, so this is if we have nth order polynomial as given in equation 4.53 in Newton's form. So, and you were asked to generate all of the polynomials of order first order till the n-1 order. We can generate them directly from this format. We can generate them directly from this format. So how? Assume that we want a first order. For first order, we take only those terms. This is the first order polynomial. Assume that we need a second we extend and take this. This will be the second order polynomial. Third, we add the term and include all of the previous term. So this is what we mean that if we have an nth order polynomial, all polynomial of degree m, which is less than n, can be taken directly from the original nth order, but the only restriction is that it should be written in this form, not in the polynomial format general one. Okay, and if we have any n+1 data points, okay, and we want to generate nth order polynomial. If we have any n+1 data points and we will generate an nth order polynomial. This final polynomial of degree n, okay, will be the same, will be unique regardless of the order of the data points, since I mentioned that the polynomial is unique. And the final feature is that higher order versions of the polynomial can be developed by adding only a single term to the next or lower order. Assume that for this equation, this is the nth order, and assume n was like the third order. Assume that the third order, I am not satisfied with it and I want to go to the fourth order. So what should I do? I will use all of the terms of this polynomial, and I will add a single term representing the fourth order finite difference and all of the multipliers in that term. So when switching from any order to the next higher, we will add a single term to the previous lower order polynomial. Let us take an example in this regard, which is example 4.11. So we have 3 data points, base points x1, 1, 4, 6, and this is their corresponding f function values, and this is the values for the len function that we previously covered in the linear interpolation, and it's required to fit a second order polynomial, and within we are required to estimate the value of the polynomial at x is equal to 2 and compare it with the exact value of len 2. So here we calculate this b naught, which is equal f of x naught. This is the first order divided difference. This is the second order divided difference. And finally, this is the formula of the second order or the quadratic polynomial. This is f2. Okay, and if we substitute x is equal to 2, then we will get this value. And this value, it has a relative error of 18.4. Okay, and if we pay attention to this figure, okay, so in this figure, the black one is the original function len x, and this is the second order polynomial, okay, while the dashed line, this dashed line is the first order polynomial between 1 and 4, which was the best in the previous example. So and we want to calculate the value of 2. This is the value of 2 here at 2, x is equal to 2. So these are the true value here, and the quadratic estimate and the linear estimate, and it's obvious that the quadratic estimate is closer to the true value than the linear estimate. Okay, now let us switch to the next example, example 4.12. Here we increase the number of data points to 4 points. We increase the number of data points to 4 points, and those are the 4 points. And we want again to estimate the value of the polynomial at 2 use third order interpolating polynomial. So this is the general form of the polynomial, and these are the 3 first order divided differences. These are the 2 second order divided difference, and this is the only unique third order divided difference. And if we substitute the corresponding divided differences, we get this equation. And if we calculate or substitute x is equal to 2, so we get this value for the function of the interpolating polynomial at x is equal to 2, and it has a relative error of 9.3, and this figure shows that our approximation is now very close to the true value. So in the next example, we will use again the same data points. An example, this 4.13. We will solve the same example, the previous one, but we will change the order of the data points. We will change the order of the data points. Okay, so don't forget that when we change the order of data points, we change them as pairs, as I mentioned previously. Okay, so the order has been changed for those 4 data points, and we want to re-estimate the value of x equal to 2 for the new generated third order polynomial. So this is the table or hierarchy of divided differences: 3 first order, 2 second order, single third order, and this is the polynomial, and here it's the value at is x is equal to 2, and this epsilon t, which is equal to the same values subjected to round off errors. So here a very good and important note, it's written: the result obtained for in this example is the same as the result for the previous example up to 5 significant digits. So the error in the last 2 digits is due to round off error. If we don't have any round off errors, then we will get the same answers. And how can we verify? We can verify it if we increase the number of significant digits to 16 or something like that, higher than this, then we will get the same answer. So it's supposed that if we change the order, the same final polynomial will be obtained, subjected to round off errors, because when we change the order, the round off errors will be different. Okay, the round off errors will be different, and this is the only source of errors between if we solve it using a certain set of order, and then after that we solve it using another order, a new order. So these are general notes. Finite divided differences, they represent approximation for derivatives, and this I have mentioned this fact previously. The second note is that if the true underlying function is an nth order polynomial. What do you mean by this? That assume that we have, like, for example, a third order polynomial. F of x was third order polynomial, like 1 plus x plus 5x squared plus 10x to the power 3. This is third order polynomial. Then assume that from this function we have sampled, or we have taken 4 data points. 4 data points from x naught, f of x naught, till x3, f of x3. And then we have used third order interpolating polynomial based on Newton or any other method. Then we have generated this f3 of x based on Newton. So f3 of x that's generated from the Newton should be the same as the original one, subjected to round off errors. If we assume that there is no round off errors, so f3 of x should be the same original f of x. So theoretically speaking, f3 of x should be as the same as f of x, and this what we mean by this point. If the true underlying function is an nth order polynomial, and we generate an nth order interpolating polynomial based on sampling this function using n plus 1 data points, then they should be the same, yield exact results. Okay, the next comment is higher order versions of polynomials can be generated or developed by adding a single term to the lower order equation, and this facilitates that computer programming for the case when we don't know the order of the polynomial in advance. If the order of the polynomial is unknown, then this scenario is very nice. So we keep adding new terms, and we determine the point of diminishing return according to this case. That assume that we have a value, a desired base point of xd. So we calculate nth plus 1 polynomial and substitute xd in it, and the lower one fn of xd. So we have 2 polynomials. One is n plus 1 order and one is the nth order. So in case, assume that we don't know the order of the polynomial in advance, okay, or of the function. So like we generate first the linear polynomial and the second, and we compare. Does the second, like this as given here, is the second order polynomial, the difference between the second and the first at xd, is less than certain threshold? If it is not less, then we keep adding. So we go to the third, calculate the third, and we compare the third with the second. If the difference between the third and the second is still larger than the threshold epsilon, then we go to the fourth. And at the fourth, we calculate it. We check the difference between the fourth and the third. Okay? And at xd, if the difference is less than epsilon, then we quit and we say the fourth polynomial is the best, and we don't keep changing or keep increasing the order at this point, after this point. Okay? So lower order differences are used to compute the higher order difference. And this is what I have mentioned previously, that if we want to calculate the second order, it will be based on two first order. If we want to calculate the third order divided difference, it will be based on the calculation of two second order divided differences. Okay? And this final point or note is that regarding the positioning of the data points or the sampling. It says that the positioning or the sampling of the data points is very important. Okay, so assume that we have a function that we want to sample. Assume that we have a function that we want to sample this function, okay, between like x is equal to 1 and x is equal to 5. Okay, so we have certain function that we will sample within the range between 1 and 5. And for this purpose, we have generated two cases. The first case is like fourth order or 5 points. Like we calculate at 1, the base points, 1.5, 2, 2.5, 2.9. These are the base points, x values, and for each x we calculate the value of the function. And the second case, we used only 3 data points. Okay, the 3 data points has base points of 1, 3, and 5. And we are interested in finding the value of the function at x is equal to 4.5. So, if we pay attention to this first scenario, all of the data points, they are shifted to the left side of the interval, while it does not cover the interval between 3 and 5. From 3 till 5, it does not cover. While those 3 data points, they cover the left, the middle, and the right. So, the value of the function, this function, which has lower data points but distributed at x is equal to 4.5, will be better than the value of this polynomial, which is of order 4, okay, at x is equal to 4.5. So a second order polynomial will have a better approximation than a fourth order polynomial. Why? Due to the wise positioning of the data points. Here they are distributed in this case. 1, 3, 5. While here they are lumped. They are beside each other, and there is large interval or the area of interest. It's not covered in our case. So this is what we mean by the last point. The last point means that if the positioning of the data points is very crucial. It's very important. This means that they should be distributed about the interval between x minimum and x maximum. And for example, a quadratic polynomial with distributed, as I mentioned here, might be better within this interval, x lower and x upper, might be better approximation than an polynomial of order 4, but with collected points, and those points, they are shifted away from the point of interest where we are interested in calculating, like for this example 4.5. So this is what we mean by those notes, and we will stop in this lecture at the second method of generating the interpolating polynomials, which is the Lagrange interpolation method. Okay, so in the next lecture we will cover this procedure because we have covered completely the Newton divided differences method. Thank you.